Hello, everyone. I'm Kofi Boakye, and I'm an applied scientist within the Applied Technology Group at Pinterest. It's now my distinct pleasure to introduce the next portion of our program, the Lightning Talks. We have 5 really exciting talks lined up for this session. The moderating of the talks will be split between me and my colleague Sindhu Raghavan from Ads Relevance, whom you'll meet a little later. Each speaker will present for approximately 15 minutes, followed by a 5-minute Q&A period. Please be sure to add your questions to the public chat during the talks. For our first lightning talk, we have Rex Wu, who will be discussing how we leverage the large-scale data at Pinterest to develop state-of-the-art models for product visual search.
Hello, everyone. My name is Rex. I'm here on behalf of Visual Search team to present our latest progress on visual embedding training. We call it Unifying Embedding V3, medium scale pre-training with hybrid vision transformers. First, I want to introduce why is visual embedding important and how is visual embedding used at Pinterest. First, visual embedding powers visual search engines at Pinterest. We help our users take actions on the inspirational images they found on Pinterest or found the camera photos. We either recommend other visually related contents on Pinterest, or we find the product they are interested in from the image. So to give you a sense of the scale and potential impact we have, we serve more than 30 million visual search requests daily among more than 12 million daily active users. These numbers make us one of the largest visual search service in the industry. And secondly, visual embedding is the foundation on which we build dozens of image classifiers at Pinterest. Many of you may know that building image classifier from raw pixel image is expensive. It often requires GPU machines for training and for inference. If we have visual embeddings available for these images, it is easy and it is cheap to build lightweight image classifier on top of visual embeddings. These image classifiers provide many important signals for Pinterest. To give one example, recently, to make Pinterest a more inclusive place for all our users, we launched hair pattern classifier to help our users filter the content based on their hair patterns so that they can see the most relevant result to them. And finally, visual embedding is also used in many downstream applications as an input signals. For example, our famous xSAGE embedding, trained with graphical neural network, takes advantage of visual embeddings to get the signals from the image. Visual embeddings support dozens of use cases at Pinterest. Now, I will give you some background on how we train our user visual embeddings to support all our use cases, and how large-scale pre-training and transformer model can help us improve all of them. So how do we do it? How do we support dozens of use cases? One nice solution is that we can train one embedding model for each use case, but it will be very expensive and hard to maintain. And another solution is to set up multi-task training. That's what we do. To have one single unified embeddings that's trained with all the tasks we care about. I will defer the details of how we set up this multi-task training to our 2019 KDD paper titled Learning a Unified Embedding for Visual Search at Pinterest. So in addition to cost savings, we found that multi-task unified embedding training has more benefits. The first one is it actually has better performance as compared to specialized embedding trained just with each task. Secondly, when there's an important downstream client want better performance out of unified embeddings, we can just simply promote their task and add their task to unified embedding training to improve their performance. Next, large-scale pre-training especially combined with large model, has had tremendous success in both natural language processing and computer vision. At Pinterest, being a predominantly image-based platform, we have an incredible opportunity to push the envelope in pre-training. The only question is, how can we curate the content to form a high-quality pre-training data sets? We will answer this question in a later presentation. Next, I just want to give a very brief background on transformer architectures. Transformers is introduced in 2017 in a paper titled, "Attention is All You Need." Since then, transformer model has taken NLP field by storm. In 2019, a transformer-based model called BERT is introduced and achieves state-of-the-art on almost all the NLP tasks at the time. One of the key features of BERT is that it performs especially well when it is pre-trained on large-scale datasets. However, the success of transformer-based model hadn't really spread to computer vision field, not until this year. In iClair 2021, in a paper titled, "An Image is Worth 16 by 16 Words," it successfully trained a BERT-like model for computer vision tasks and achieved the state-of-the-art results. The one key difference between Vision Transformer and BERT is that instead of text token inputs, Vision Transformers take image patches as input to the model. And like BERT, Vision Transformers also enjoys the most performance benefit when it is pre-trained with large datasets. So we learned that large-scale pre-training plus transformer model can deliver state-of-the-art performance. Next, we will dive more deeply into how we collect a billion plus datasets from Pinterest content. So to collect such a datasets, we use a mixture of heterogeneous Pinterest text signals. First step, we use an in-house system to predict annotations for images and filter our low-scoring ones. Second, we select only those annotations that can be distinguished visually. For example, base designs will be filtered out. Third, we cluster the annotations to reduce cardinal label space. Note that two annotations can be clustered into one single clusters. For example, jaguar and panther both will be clustered into animal class. And also an annotation can belong to multiple clusters. For example, jaguar can either be an animal or a car brand. And finally, not all annotations are equally important based on the applications. Therefore, we filter out the annotations based on our category of interest. The resulting datasets, we call it annotations 1.3 billion datasets. It has more than 18,000 classes, and on average, we have about 3 labels per image. And since we have multiple labels per image, the objective we use during pre-training is multi-label softmax loss. To train a vision model with billion plus images requires some infrastructure support. We highlight some of our work. First, we adopt Kubernetes-like training platform to facilitate multi-node training. And second, we implement streaming data loader so that the entire dataset don't need to be on a local disk to start the training. The dataset can live on the cloud and can be streamed on demand during the training. Finally, we use mixed position training to increase our training throughputs. In the figure, you can see the training throughput improvement when we go from FP32 to FP16. Next, I want to introduce the transformer model architectures we use, called hybrid funnel vision transformer. This model architecture is very similar to the original vision transformer model. So I just want to highlight two key differences. First, for the input to the transformer, instead of using image patches, we use the output feature map of a convolutional neural network model. Hence, we have the prefix hybrid. Second, for the transformer body, we use funnel transformers that's introduced in NeuralRips 2020. In the original vision transformer, there's a constant number of tokens for all the transformer layers. But for funnel transformers, the deeper we go, the less tokens we have for the transformer layers. Empirically, we found that this model architecture works better for us. Then we run a Bayesian study to show that how this vision transformer model compared to the CNN one. So the Bayesian study is on pre-training dataset size. In this figure, you can see on the left-hand side, when we are on the smaller pre-training data regions, CNN model perform better than both VIT models. However, as we have more and more data available for pre-trainings, the large VIT model start to outperform the CNN model. This figure also showed us that the larger model can better leverage the larger data size we have. And finally, I want to share with you some results when we go from V2 to V3. To recap, the two models we are comparing here are Unified Embedding V2, which has a CNN-based model, and the weight of those models is from a publicly available pre-training weight. And for V3, the model architecture we choose is a transformer-based model architectures. And this model is pre-trained with the 1.3 billion annotation datasets we collect from Pinterest. In addition, this Unified Embedding V3 model has 6 additional tasks. Here, I'm just showing a laundry list of the offline eval improvements we have for V3 compared to V2. The short story is that the billion scale pre-training combined with transformers model improve all our offline metrics. What's more exciting, at least to me, is that how this model performs in real life. So earlier this year, we ran an AB experiment and deployed the model to productions. Here is the graph showing before and after the model deployments, how our user engagement metrics changes. You can clearly see the user engagement metrics went up after the model deployment. But to leave you with some takeaways, those are the learnings we have at Pinterest. First is that the multi-task visual embedding training setup gives us a lot of benefits. For example, if you have one improvement in the backbone model, you can easily propagate those benefits to all the tasks you care about. Secondly, if you want to improve a downstream application to your visual embedding models, you can simply add those downstream tasks into your embedding training. Thirdly, we know that billion scale pre-training plus a large model has the state-of-the-art performance in many academic datasets. Here we show that it also delivers a pretty good wins in the industry setting in a real-world application such as visual search. Thank you so much for listening. If you are interested in the evolution of our unified visual embeddings, here I list out 3 papers details for each version, what did we do, and what is the experiment we ran. If you have additional questions, I'll be happy to answer them in the following Q&A section. Thank you.
Thank you for the presentation, Rex. It's really encouraging to see that with Pinterest's unified embedding model, we can add additional tasks and see improvements across the board and, most importantly, in downstream applications. We now have Rex here with us, who will be participating in a 5-minute Q&A session. Thanks for joining, Rex.
Hello, everyone. Hello, Kofi.
So we can start off with this question here that was posed from the chat. How well do image features generalize to new tasks? For instance, do tasks included in the feature pre-training see better performance than tasks which are unseen during the embedding training process?
That's a good question. The short answer is yes. If we use the embedding for the test that we pre-training on, then we see a better performance. So that's why there is a benefit of setting up embedding training in a multi-task fashion, so that when there's a test, you want the embedding to generalize well. You just add those tests into your embedding training. I think there's a second part to that question is that how can we make sure our embedding can be well generalized to the task it hasn't seen before? Yeah, I think this is our active research topic that we want to see how we can structure our training such that it can also generalize well to other tasks. But for now, adding those tests into our unified embedding training is the surest way that we can guarantee the model can generalize.
Great answer. Another question from the chat that was posed. I'll just quote it verbatim. Multitask embedding sound cool, but how do you figure out what set of tasks grouped work together? What if lower level details are missed due to what I presume is the grouping of certain tasks?
Cool. Also a great question. Right now, we don't do any grouping. So all the tasks are forked from unified embedding training, and we add multiple different heads associated with each tag on top of unified embedding. And the reason why we want to do this is we want our unified embedding to capture all the information necessary for each one of the tasks, so that when we have the embedding available for the image, other downstream customer can just take the embedding and train their task of interest with good performance. So that's why we don't really do any grouping here. And as for the second part of the question, what if some information is lost in the embedding? So there's sometimes it happens. We cannot avoid it. And one of the best way to fix that is by, again, adding additional text. I can give you one example. So recently, actually, Kofi is working on image quality tests that may require some low-level image features that are not present in the unified embedding. So by adding this image quality task, we can make sure all the relevant information can be present in the final unified embedding for other people to use. So we will just add those low-level image tasks to the unified embedding to make sure those information exist.
Great. Excellent answer, and thanks for the plug. Unfortunately, we're short on time, so we're going to have to end things there. But thank you very much, Rex. Up next, we have Andrew Zhai, and Andrew will be presenting xSAGE, Pinterest's cutting-edge application of representation learning that spans everything from search and shopping to user modeling.
Thank you for coming to our ML Lightning Talk. Today, I have the pleasure of describing some of the work we've been doing in representation learning embeddings of content, search queries, and users that over time have been shown to simplify and improve ML at Pinterest. Pinterest is the home of inspiration. People come to Pinterest to find ideas, such as what recipe should I cook for breakfast this morning, or looking for that perfect sofa that fits your aesthetic designs for your next remodel. Our users are able to find these ideas through our personalized recommendation and search systems, generating endless feeds of diverse content like this one you see here. Pinterest is quite complex. A user can come to Pinterest and interact with many types of ideas. Some are organic content, like this broccoli with garlic sauce pin that links to an underlying detailed recipe website for more information. Or I can view this idea pin, content from our creators made just for Pinterest, with pages of images or videos showing me details on how to make this dessert. Or I can purchase this product, or I can watch this ad. We see here that content on Pinterest has either a person or a business behind it. I can follow a creator that I like who always publishes great content that I personally enjoy. Or I can track this merchant for their new lines of products to purchase. And similarly, look up brands that showed me an interesting ad that just caught my eye. At Pinterest, we build recommendation products that help users complete each of the edges here. We help you follow creators that you like and discover products that you're inspired to purchase. We also need to make sure Pinterest is safe, that we don't recommend you pins that are not safe for our users. So how do we make sense of everything? Like, how can we simplify ML at Pinterest so teams can build great solutions faster and not have to start from scratch every time? That's where representation learning comes in, translating these vague concepts of pins and users into embeddings, something much easier for our ML models to leverage and understand. I'll be describing 3 of our representations today, some of our most important ones, such as starting with content. This one is fairly important. We'll see how a strong content embedding makes it easier for us to learn strong search queries and user representations as well. Pins are our main content, and we see it has many components, the most important of which is the image or video. But we also do have a title, the user that created the content, as well as this more indirect concept of a graph. One graph that we found to be very important at Pinterest is the pin board graph, where users have manually curated their boards. The power comes from different users putting the same content into different boards. For example, we have kiteboarding and snowboarding. The same content put into these 2 boards have a stronger prior of meaning, for example, outdoor sports. If you think about this relationship at scale, billions of pins and billions of edges, that's a really powerful relationship that helps us understand content better. Our hypothesis is that the graph is quite important to understand content. When we were thinking of solutions for a good comprehensive content embedding, we needed one that works for graphs, for text, as well as for images. And we see that a graph neural network fits this paradigm pretty well. Given the pinboard graph, we convolve over it with nodes represented by these multimodal features of text and image. One thing to consider for Pinterest is that our graph is really big. We have billions of nodes and tens of billions of edges. Here, we're interested in inductive learning. We don't want to represent a node just by their ID. We want to represent a node by their features. And this is because we get new content on Pinterest every second, and we need to make sure we can generate an embedding every second. A naive transductive model would require us to learn an ID for every node, where an ID is represented as an embedding in a lookup table. And this doesn't generalize for us. Instead, because we represent a node by features, we can train our model, our GNN, and whenever a new content arrives on Pinterest, we look up its image and text embeddings and are able to simply leverage the model we've pre-trained to generate our new embedding. Our GNN model has changed over the years, has evolved over the years. We started with two-hop neighborhood sampling on the pinboard graph, but now we actually leverage this random walk-based solution instead, where given a node, we generate around 50 neighbors, where each neighbor is sorted by the visit count, which approximates personalized PageRank score. To understand our ML problem setup a bit more, let's just start simple and not even consider the graph. Here, we want to use a pin's image and text embeddings alone to learn a good content embedding. And we see to do that, all we do is encode these features in a multi-layer perceptron that we pass through an LG normalization to get a normalized embedding. We then want to learn meaning for that embedding using a metric learning loss. I won't have too much time to go into details on the metric learning loss itself, But at a high level, what we do is that we have data telling us, given the query pin, which pin should be similar and which pin should not be similar. Our loss function encourages the embedding to learn a similarity function that reflects this. And there are many methods to accomplish this, but I'll leave the references here for more detail. So let's dig into the graph part of this problem. Overall setup is still the same, but instead of just using a node's image and text features, we now have 50 neighbors. Each neighbor is also a node, which has its own image and text and features. So we have multimodal features for 51 nodes in total, 1 for self, 50 for neighbors, that we summarize through a transformer that produces an output that we pass through a multi-layer perceptron, to normalize to produce our embedding, and we use the same metric learning loss. This is how we train our graph neural network to produce our content embedding. We see that graph neural networks produce the best content embeddings at Pinterest. On the left, we have some internal data sets measured over many days to evaluate how XSAGE performs, especially because the graph is dynamic, it changes every day. We see here, higher is better, and compared to using a visual embedding by itself, a text embedding by itself, there's also a line that we didn't add here, which is an MLP on top of visual and text, combining just those two features alone. We see that XSAGE gives us the best performance. So using the graph as well as the multimodal features together gives us the best performance. And we've had a lot of success with XSAGE, over 70 launches, which is a lower bound because we actually track these things manually, like through a spreadsheet. And we use XSAGE now for many parts of Pinterest whenever we need to understand content, like recommendation systems or trust and safety to classify content into safe or not safe categories. I spent a lot of time going into the details of XSAGE because it's quite important. I'll show you now that XSAGE helps us learn search queries and users effectively as well. Essentially, what can we do now that we have a strong content embedding? Let's look at search queries first. The problem statement here is that given a search query, which is a text input, we want to produce an embedding. What does this mean actually? How do we learn this representation to be meaningful? Oops. We have image search on Pinterest, where users types in queries like chicken recipes and gets a feed of results. We can actually get a lot of weak supervision from this. Some examples: a user is looking for kitchen taps and sinks and purchases this specific faucet. Or a user repins this dog line drawing after typing in animal line drawings. Or a user clicks this recipes after typing in Whole30 shrimp recipes. You can see here we have a lot of different types of actions, and some actions types are more informative than another. For example, purchases is a pretty strong indicator of a positive relationship between this query and this content, because users need to purchase with money, which is a lot sparser of a action compared to something, say, like a repin, which is for free. Well, that's sort of the overall intention, right? Can we use this positive feedback? Can we use the fact that a user has told us that this search query and this piece of content has some positive relationship to help us learn the meaning of search queries? This is the overall setup. It's really quite similar to the XSAGE training. We have our metric learning loss on the positive side, and as well as negative, we have a XSAGE to represent the content, the pins. Here, we use random pins as negatives because we have billions of random pins. And during training, say if we sample 1,000 random pins out of 1 billion, the chances of them being relevant to this specific search query is quite low. On the query side, we evaluated many different approaches for the text encoder itself and ended up using this Dilbert architecture because it actually had the best trade-off of performance with serving cost. We see on the left here that XSAGE produces the best search query embeddings compared to visual or text alone, also compared to both. We can see here we have our visual. When training the previous model with only visual features for the content side, we have this baseline performance. Training only text features, we have this baseline performance. And when you use XSAGE, you get the best performance for both product search as well as organic search. We had over 10 launches for this as well in the search stack across different verticals. One highlight here is that we improved long clicks and impressions on products by 11 and 8% respectively on product search through using xSAGE directly as retrieval with pin save on the content side. The reason why we can do this is that we learned the embeddings, if you remember, with metric learning loss. And this gain was quite significant. So let's ask the same questions for users. How do I learn this user embedding? We had a prior work here that gave an answer where we took the user activity sequence of the user and represented each action by the content embedding by PinSage. We then did an unsupervised on-the-fly clustering on top of PinSage to generate multiple clusters. When you visualize the clusters, like here, where each row is a different cluster, we found that each one of them had some semantic meaning. We then take the medioid of the cluster, that becomes our user embedding. And now we have a way of going from one user to multiple user embeddings. And this was actually quite effective. It seems like a simple approach, but we had over 10 plus launches with this algorithm. And one of the most significant ones we had was this 3% increase in home feed engagement volume. So home feed is the personalized recommendation system that you see when you enter Pinterest, and it powers around the majority of engagement on Pinterest. So a 3% increase there was quite significant. Of course, now we want to actually try a supervised and deep learning approach. How can we take that user sequence and learn a user embedding? We aim for one user embedding here because one, we wanted to start simple, but also because we learned that multiple user embeddings actually had some challenges when integrating it into downstream systems like ranking. For this work, we first produced the entire pin activity sequence for a user across all of Pinterest for an entire year. Here, maybe a user was on related pins, for example, and then clicked a pin. Maybe 2 months later, then that user is on home feed and repinned another pin. And then maybe 8 months later, a user is on image search and repinned this other pin. And maybe these actions have nothing to do with each other, or maybe they do. The model will be the one to learn these relationships. Some users also have fairly long sequences. Some users have 10,000 actions or 100,000 actions. So we have to deal with that as well. To train our model, we first randomly split the sequence. This is done per user with different splits. We then encode the last 255 actions to generate one user embedding. Each action here is represented by features like PinSage, action type, timestamp, relative timestamp of actions, also which surface an action originated from. And we encode these actions through a transformer to produce that one user embedding. And then use this user embedding to predict actions 14 days in the future. This is the high-level architecture that we described. We use a transformer again to encode the last 255 actions to summarize into one user embedding. We use the same metric learning loss with positives and negatives represented by PinSage. It's really quite similar to the xSAGE setup, if you recall. Here, the positives and negatives are both pins. The motivation for random negatives is the same as what I described for xSAGE. And the intuition for the positives is that the content right after the random split that you take should be closer to the user embedding than, say, random negatives, right? Because we randomly split that user sequence, so there should be some continuation of the events. Our supervised method was actually quite effective. We see on the left, compared to the previous approach, we were able to do better on our offline eval with just one embedding compared to the previous multiple embeddings. But more importantly, when we actually tried this method in home feed ranking, where we used this new model as a feature in ranking, replacing the old one, we were actually able to get quite significant lifts. About 1 to 2% increase on time spent on Pinterest, 3% increase on engagement, 3 to 4% increase on engagement on Pinterest, as well as a 2.6% reduction of hides on Pinterest, which indicates that we're showing content that a user likes more now. And this sort of lifted everything we cared about at Pinterest as well. While I was able to describe our work on content, search queries, and users today, there's a lot more going on in the representation learning space at Pinterest. For example, we need to understand videos. We need to understand creators as well as products and also interests. And we're always thinking about what's the next step? What's the next step function technology improvement we can make to really have impact at Pinterest? Here are some of our thoughts. We see, for example, that we actually want to use larger and larger models. Not really that much of a surprise if you're following the NLP literature these days. But we know that models' performances, we know that models like xSAGE are not saturated by parameter size, but we know that the return is actually logarithmic. So we need an order of magnitude improvement to really get more impact. I described how important our content embedding is, and it's actually quite challenging to iterate on GNNs at web scale. But we do want to explore heterogeneous graphs beyond the bipartite pin board graph, because while pins and boards are important, we have so much more information. Think of users, creators, products for node types, and purchases and follows as actions. That would give us so much stronger priors to understand the entire Pinterest ecosystem. And we will, of course, continue investing in core machine learning, finding better ways to do metric learning, better or more efficient architectures than the transformers today, and also how to best do these multimodal learning at scale. Should we fine-tune the visual embedding end-to-end? Should we fine-tune the text embedding end-to-end? What's the best way to do that? If you're all excited about this work, please join Pinterest and help us build the home of inspiration for everyone. Lastly, I want to just thank the awesome team that does all the work, both the core folks as well as the many folks at Pinterest whose contributions have made representation learning such a big success. And thank you all for listening to my talk. This is my last slide, and that's it.
Thanks, Andrew. From the talk, we can really see the power of representation learning, in particular, the use of state-of-the-art transformer models to improve the experience for Pinterest users, creators, and shopping partners. Now Andrew is here with us to briefly answer questions from the audience. Welcome, Andrew.
Hello. Hope you all enjoyed the presentation.
Yeah, definitely. We have a few questions from some of the audience, and I'll ask those now. The first question is, what metrics do you use to measure the quality of representation?
Oh, that's a pretty good question. It's not a simple answer, actually, unfortunately. So we have both quantitative and qualitative measurements. Quantitative measurements are offline evals, such as like recall, where we take the recall of nearest neighbor performance over the engagement data with the random negatives. That gives us a number, and we sort of track that as our primary metric to optimize. Qualitatively, we look at the nearest neighbor results. So all of these approaches are learned with the metric learning loss. We can see the results and sort of tell if anything funky is going on. This is really fast cycle of offline evals, where every time we train, we have these numbers automatically. But then we take the cycle maybe every month or every quarter to run the online A/B experiments where we actually see, like, are our offline metrics right? Are we still on the same page with online performance?
Okay, so it's a combination of offline and online eval metrics typically. Great. Second question. If your encoder model requires 50 random walk pins, how does this generalize to new pins that don't yet have any graph edges from the pin boards?
So our model actually takes a maximum of 50. So not, even when you do the random walks, it's not guaranteed that you'll always get 50 results. In the case that we actually don't have 50 neighbors, the rest are just padded, zero filled. Previously, we've also explored using dropout to artificially remove some neighbors so that this like self feature by itself can be strong and sort of without any neighbors at all.
I see. Another question from the audience. If random pins are negatives for metric loss, then is there a risk that they are too easy? Can you potentially have, too easy random negatives when ideally you'd want medium to hard negatives somehow?
It's a good question. Negative sampling is probably the hardest part of these metric learning approaches. I didn't have time to go over it in the slides, but we actually do use in-batch negatives as well. You can think of these as, instead of pure random from corpus, they're at least impressed results. So they're somewhat popular recommendation systems, somehow like them previously in the past. Another detail here is that for every single query positive pair, we actually have around like 50K negatives. So it's actually quite a large size. And that helps, within that 50K, there's usually at least some medium to hard examples, and those help the learning a lot as well.
Okay. Well, that concludes it for the Q&A session. Thanks for joining us, Andrew.
Thanks for having me.
So up next, we have User Journey Modeling on Pinterest Ads, presented by Yiping Xu and Ning Zhang. Here's the presentation.
Hello, everyone. Thanks for joining us today. In this lightning talk, we are going to share our experiences for user journey modeling on Pinterest ads. My name is Yiping. I'm from Ads Ranking team. I will present this talk together with Ning from Ads Infra team. Our users come to Pinterest to explore ideas and inspirations based on their own interests. The goal of this work is to serve personalized content to users by exploring their journey in Pinterest app across organic and ads content. We want to build an ads engagement model and corresponding serving infrastructure that is able to capture such latent interest behind the engagement history. First, let me briefly introduce the baselines in this work. Here is the overview of ads engagement model that we launched in 2020. This model will first preprocess the input features by performing embedding lookup, normalization, and feature crossing, and then followed by several fully connected layers. On top of the fully connected layers, we have multi-tower structure to handle different ads product type in Pinterest. Using this multi-tower structure can help to isolate the interference between different ads product type without hurting each other. In addition, this model jointly optimizes multiple objectives like click-through rate and also other engagement action like good click rate and scroll up rate. This multitask and multi-tower structure not only show promising performance, but also allow us to simplify the system and save infrastructure costs for Pinterest. We don't have time to cover more details for this baseline model, but please feel free to check our engineering blog on Medium. And as I just mentioned, we want to build an ads engagement model that is able to capture the user interest behind their engagement history. So obviously, this baseline model is not able to do that. So we want to add something new on top of this model. And here is what we propose. We first collect user engagement history from Pinterest log and transform the data into sequence features. And then we build a new subnetwork to learn from these sequence features. I will introduce the structure of this user journey network later. The output of this network will be a representation of user interest, and it will be passed directly to the fully connected layer. This user journey network is co-trained together to optimize the objectives for the ads engagement model. In the first phase of this work, we focus on user short-term interest. So we collect user most recent 20 engagement events in the past 7 days. And each event is represented by a pre-trained high-dimensional embedding. This embedding is developed by our science team and has been proven to be very powerful within the company. Now we have embeddings for user engagements and also embedding for target ad. Our first solution is to apply attention mechanism on top of these embeddings. So for each user engagement, this activation function will take the embedding for this pin and the embedding for the target ad to compute an attention score. This attention score reflects the relevance between the engaged pin and target ad. We can use this simple example to understand the idea. Given a target ad about the recipe of a dessert, those engaged pins that are also about dessert or food or recipe will get higher scores, which means we want to put more attention on these engaged pins. While other irrelevant pins about home decoration will get lower scores. All these attention scores will be used to perform a weighted sampling over all embeddings. And the output of weighted sampling will be a representation of user interest. Finally, this user interest embedding is concatenated with the target ad embedding and passed to the fully connected layer of the original ads engagement model, so that the model can learn the interaction between user interest and target ad. So this is the first version of our user journey network, and we found this network structure simple but very powerful. Here are the results of this attention model. We saw significant improvement for AUC and loss in offline evaluation. And online A/B testing also showed very exciting results. We even saw non-trivial positive movements on Pinterest top-line metrics. Right now, this model is serving major traffic for Pinterest ads. In the same time, we are thinking about more improvement on the attention model. How about we use more user events to represent user journey? Also, right now, we only use a pre-trained high-dimensional embedding feature. How about we add more features and let the model learn native embedding? Also, the attention model does not consider timestamp or the order of the user events. What about we build a time-aware model? So with these ideas in our mind, in the second phase of this work, we collect 100 events for each user in the past 3 months. And each event has several categorical features and also timestamp features. And for the second version of the user journey network, we build transformer to learn from the sequence of user events. For each event, the model will learn embedding for categorical features and also learn positional embedding from timestamp feature. All the embeddings for a given event will be concatenated together and passed to the transformer. The transformer part is a typical transformer encoder. It has first multi-head self-attention layer, and then followed by residue connection and layer normalization. After that, a point-wise feed-forward network is applied, and then finally, again, the residue connection together with the layer normalization. On top of the transformer encoder, there is another multi-layer perceptron. And then the final output of this network will be passed to the fully connected layer of the ads engagement model. So this transformer model is our second version of user journey network. And here are the results of the transformer. Compared to the first version in offline, we saw both AUC and loss are further improved. And in the past 1 month, we started the A/B testing for this new model. And the result again show very promising gain in ads engagement metrics. There are several practical lessons we learned from this work. First, we found the real-timeness of user events can greatly affect model performance. We compare the models trained with real-time events and model trained with delayed events. And the model with real-time events has much better performance. However, even the model trained with delayed events is still better than the baseline model. And some research also showed that the longer sequence of user events is very helpful to the model. Secondly, we also implement a GRU model on the same set of sequence features. And from offline evaluation, the GRU model slightly outperformed the transformer model. So we once considered to run A/B testing with the GRU model. But later we found that the latency and the CPU cost for this model is so much higher. So given the trade-off, we choose to launch transformer. But this does not necessarily mean that the transformer is not as good as GRU. Since we only implement a vanilla version of transformer encoder, we believe that there is still room to improve the model architecture as well as the loss function. Next, I will hand over to Ning to talk about how we build infrastructure to serve real-time events and how we optimize the TensorFlow serving for the transformer.
Thank you, Yiping. I'm going to talk about how two aspects of the serving. One is how to serve sequence features and what is the performance or in the inference time. Next slide, please. At Pinterest, we have a lot of different systems to serve features. For this sequence feature, we chose the user signal service to serve the features. The reason is because it can incorporate both batch processing as well as real-time processing. As Yiping mentioned that both the long-term interest as well as the real-time interest are important for the model performance. As you can see from the left-hand side, we have an offline continuous process to handle both the batch processing, the daily sequence generation workflow, to get the last 3 months of user sequence and into the batch sequence database. At the bottom, we have the front-end event systems that listen to the Kafka streams and send the real-time events to the user event KB store. Usually, the latency for that is usually from seconds to a minute. At the request time, when the user comes in, is send the request to the service event handler. And this event handler pull the user's long-term sequence from the batch sequence as well as the real-time sequence. And then they merge those two data sources based on the timestamps. Next time, please. Next slide, please. Then I'm going to talk about the model serving latency. In the picture, you can see the latency distribution in terms of P99, P90, P50. We compared two models, attention model and transformer model. The attention model is in green line and transformer model is in red line. As you can see, this is the end result of several tunings, and we can see about 3 milliseconds additional latencies to the transformer model over attention model. This is mostly due to the extra computation complexity in the transformer model. As we see that this has been optimized based on several runs of optimizations. The first learning that we've seen is the latency and CPU cost is very sensitive to the inference batch size. Because TensorFlow is optimized based on batch processing, we tested different batch sizes from 5 to 300, and we observed that the latency is not linear to the batch size. At last, we chose the batch size to be 32, which is a multiple of the cache line size, 64 byte, as well as register size of AVX 512. And this makes the batch processing really efficient. The second learning we found is the transformer model is a heavy user of matrix multiplication. And we tried a different kernel, contraction kernel called MKLDNN from TensorFlow, and that helped reduce the fused matrix multiplication cost by 40%. The third one is also related to the TensorFlow characteristic in that the first queries to the TensorFlow is very slow because of the graph optimization such as Grappler. And if we deploy a new model, we usually can see the first couple of minutes, the latency for all the queries can shoot up to like a couple of seconds. That's not acceptable for online serving. The way that we solve this problem is we come up with a warm-up queries and run these queries before the model is actually accepting live traffics. And from the figure, you can see that P99, P90 has spikes during new model deployment, but the spikes is not as high as several seconds now. With that, I'm going to hand it back to Yiping.
Thank you, Ning. So there are several future work that we are planning to work on. First, of course, we want to run more online experiments and apply the transformer to more Pinterest ad services and organic services. In the same time, we want to spend more time on feature engineering and model tuning. Because of some constraint on infrastructure cost and storage cost, now we only have several lightweight categorical features in the transformer. Also, we only implement a vanilla version of the transformer encoder. So definitely we want to explore more opportunities here. And we also consider to explore the output of the transformer as a user interest embedding feature, so that it can be used not only by the ads engagement model, but also other machine learning models in Pinterest. Last but not least, this work is a cross-team collaboration, so we want to thank all the contributors of this project. That's the end of this talk. Thank you very much for listening.
Thank you, Yiping and Ning. It's really nice to see the importance of both modeling and engineering to successfully employ ML at Pinterest scale, illustrated in this last talk. We now have together Yiping and Ning, who will be joining us for the next 5 minutes for Q&A. Welcome, Yiping and Ning. Thank you so much for that presentation.
Thank you, Kofi.
The question I have here is for Yiping. How do you distinguish different past engagement activities, such as click, purchase, etc., in the network?
Oh yeah, so we have defined corresponding features to distinguish different action types. So this is included in the user engagement level features. So for each event, we basically have user engagement related features and also pin level features. Yeah.
Great. So then the next question, I believe, is for Ning. How do you tune the serving infrastructure for performance? Do you use any principled approach like Bayesian optimization?
Yeah, that's a good question. Actually, I don't follow any very fancy theories, but majorly follow on measure first. If you have a good profiling tools, use that. And trying to get some details about the system that you're trying to profile, for example, TensorFlow. You don't have to be very expert on the TensorFlow, but you need to have some details, one level down to the knowledge that you're trying to profile. I don't know whether that's satisfy the answer, but that's how I do.
Great. Another question for you. Have you tried GPU serving?
No, we haven't. We found that the model is not that big for online serving, and our latency is very important. And GPU, we haven't tried GPU because we have the concern that the GPU is optimized for throughput, but not for latency. So that's probably later we'll try that.
Got it. So it's kind of in the future horizon.
Yes.
Yeah. Now turning back to Yiping, another question. Since the transformer includes attention itself, do we have plans to deprecate the attention and only use the transformer?
Right, that's a good question. Thanks for asking this. So yeah, at first we still keep the high dimensional feature inside attention. And right now there's ongoing work to move the high dimensional feature to the transformer. And so far in the offline evaluation, we saw that there is a big improvement again. So right now we are preparing the online experiment. But however, we expect that we will see latency and GPU cost increase because transformer can put the self-attention over all the user events. So it depends on the online experiment result to decide whether we want to deprecate the attention part or not.
Got it. So based on the output of the experiments, that will give us
Right.
guidance. Okay, thank you. So unfortunately, we're out of time for the Q&A period, but I wanted to thank you, both Yuping and Ning, for participating. And with that, I'll be handing things over to my colleague, Sindhu Raghavan. Sindhu?
Hey everyone, I am Sindhu Raghavan. I lead the Ads Relevance team in Pinterest. I will be your moderator for the rest of the session today. Next up, we have Zhai, Xiao, and Weiran Li presenting their work on optimizing purchases in shopping recommendations at Pinterest. Zhai and Weiran, take it away.
Hi everyone, thanks for coming to this presentation. I am Weiran, an ML engineer working on shopping discovery at Pinterest. Today, my teammate Zhai and I are going to share some most exciting recent developments on improving our inspired shopping recommendations. Shopping discovery is an essential part of Pinterest's journey of inspiration at Pinterest. Mission of shopping recommendation is connecting ideas to actual products that users can buy and make their lives closer to what they have found on our platform. So helping shoppers find the products to buy most effortlessly and with confidence is the most important objective of shopping discovery. There are many exciting projects in our team in terms of improving shopping experience, but with the time limitation, we will focus on our recent development on optimizing purchases, which we believe is the essence of improving the quality of shopping recommendations. And at Pinterest, we are empowered to do that since we get purchase data from tens of thousands of partner merchants. There are two primary approaches in our recommendation stack for this goal. On the one hand, we build new candidate sources and recommenders. On the other hand, we improve our ranking by adding purchase objectives. For the rest of this talk, I will go through a candidate generator that we introduced lately, and my teammate Zhai will later cover how we optimize purchases in the ranking layer. The candidate retrieval is a high recall layer in the recommendation stack where we trim millions or billions of documents to the scale of less than 1,000 for the final ranking. But since our users come to Pinterest with really rich use cases and intent, one major challenge on our retrieval layers is how to incorporate all the complexities of, say, multiple types of context, specific objectives, and non-unified definitions of relevance, and so on and so forth, all together into a generic platform in a scalable way without introducing heavy maintenance burden. We kept these challenges in mind and built a flexible retrieval framework for shopping recommendations based on collaborative filtering, or CF. Just to remind everyone that CF is a recommendation framework that crowdsources user activities like people who did this also did that, or later did that. It is pretty classic that appears everywhere, but the novelty of our work is that it is an intent-based CF, which I will explain in the next slide. The intent component is illustrated by this example of people who viewed this also bought that model, where view and buy actions correspond to different intents. When certain users viewed product I and later bought product J, the model learns the positive relation between these two products. Since we always want to drive shoppers down the funnel in their purchase journey, it is fundamentally important that our retrieval model captures this intent-based component and also preserved the time sequence in these actions. So you don't keep shoppers exploring products, but never proceed in the purchase journey. As a matter of fact, this is one of the top reasons that we have to go beyond the amazing recommendation frameworks that existed for a non-shopping context here at Pinterest. The flexibility of our framework enables us to scale these action pairs. For instance, also to who bought also bought, who saved also bought, etc. Another flexibility of this framework is that these entities could easily be extended beyond products, for instance, to brands, product types, search queries, etc. Architecture-wise, we adopted a two-tower model and chose TensorFlow Recommender as the underlying matrix factorization engine. A minimum ID-based model is illustrated in this diagram. We use co-occurring action pairs mentioned in the earlier slides as positive labels and use batch negatives exclusively in the current recipe. So dense vector representations for each product, also commonly referred to as embeddings, are learned during training time. At inference time, we fetch the left representation of the query product and do an approximate nearest neighbor search in the right representation to fetch all the relevant candidates. Note again that this model is asymmetric. Each entity inherits different representations from both multiple intent and time sequence. And consequently, you get different results querying from left to right or right to left. So we also worked on some improvements on top of the bare bone. One direction of improvement is that we are adding complexity to each single tower, where we hybrid both ID-based and feature-based inputs to balance memoization and generalization. Features we add are also flexible, as it could be both raw or pre-learned. We're also leveraging multi-test learning to train a unified multi-representation for a single entity from one job. Another benefit from the multi-tests is that it makes the engagement graph effectively denser from combining multiple types of positive labels. The model is thus able to transfer knowledge and optimize the representation learning. The value from this work is also multifold in our related products recommendations. First of all, we observed a huge increase in overall engagement after we added this candidate source. Secondly, it enabled faceted results wrapped as standalone recommendation modules based on interpretable themes. For example, this people also bought or frequently bought together modules. We can see from the example here that this framework successfully introduced diverse results to the page, not only substitutes of the original products, but also some complementary. But there's also some learning and challenge in this work. Results from this model, especially the complementary ones, are sometimes irrelevant. This is primarily from model input, so we find it very critical to massage the training data in the right way. But unfortunately, we do not have time to discuss it in this talk. So next, I will hand it over to my teammate, Zhai, who's going to talk about the ranking layer.
Thanks, Weiran. Next, I will introduce how we optimize purchase in product ranking phase. At Pinterest, we first have an engagement-based ranker. Its objective is to optimize engagement, such that the products on the top are most relevant, engaging in the given context. There are different types of engagement. Close-up meaning tapping onto the pin to take a closer look. Save means saving the pin to a board. Click means clicking through the pin to visit the clicked website. They are all important engagement types to help us understand users' intention. We leverage user engagement data to train an engagement-based ranking model to predict the probability of different engagement types, given the query product and the user. We use multi-head DNN model and constructed by grouping all these features and crossed features in the fully connected layers. The output of the model have 4 output heads, each corresponding to 1 engagement type. From the multi-task model, different objectives can borrow the knowledge from each other by sharing the previous layers. The multi-head drives significant gains in the click-through rate and long click-through rate in Pinterest, but also lay a great foundation when we explore another engagement type, conversion. After the close-up and the clicks, user could transition to the next phase of shopping funnel to take purchase action offsite in the next few days, such as browsing the pages, add items to carts, and checkout. These are also known as offsite conversions. Existing recommenders are limited in their ability to drive conversions as they are currently optimized for engagement. So a strong level that we have available is to start optimizing the final ranking for conversions. Eventually, we want to estimate the probability of checkout given impression, which can be approximately reasonably combined as a multiplication of two terms and predict them separately. In this formula, the probability of click given impression is approximated by multitask model shown previously. And the probability of checkout given clicks is learned from a new shopping conversion model, which I will cover more in the next few slides. Finally, the final ranking score is a weighted sum of the engagement score. One of the challenge of the shopping conversion prediction is the data sparsity. So we don't choose to model the probability of checkout given impression directly. Instead, we try to predict the checkout given clicks and the probability of click given impression as separate tasks. This independent modeling can help deal with the data sparsity from a modeling perspective. Second, we utilize as much data as possible from checkouts data attributed to both shopping pins and non-shopping pins to increase the training data volume and leverage information from each other. The data imbalance problem is very common in the conversion training dataset. We heavily downsample negative labels by randomly sampling from the clicks data to construct a relatively balanced dataset for model training and apply calibration layer to correct the predicted score. Another key challenge is the data selection bias. Our training dataset only contains clicks data, while we need to predict the conversion scores for all impression. Here, we partially rely on the engagement model to predict the click-through rate from the impressions. The data can also be biased because we downsample negatives, so we might not cover enough merchants into our training dataset. Or our training dataset can be dominated by some of the major merchants. So we try to optimize our negative samples by increasing the positive to negative ratios and apply stratified sampling from the merchants. Also, the positive and the negatives are sometimes hard to differentiate from each other, since purchase is quite personal and is associated with many factors. To tackle this problem, we do include the dense and the sparse vector from user pin level and the requested contextual levels. Overall, a modeling method is very straightforward. We train a lightweight TensorFlow model to predict the probability of conversion given click by treating it as a binary classification problem and using pointwise approach and the cross entropy as the loss function. We start with an embedding projection layer for the sparse high-dimensional embedding using a hashing encoder to transform categorical features into numerical vector. Then we concatenate all these features and pass them through a few dense, fully connected layers before outputting the conversion prediction. Shopping conversion models has been experimented in quite a few places in Pinterest. So we observed a huge increase in checkout rate and gross merchant volume in product detail page. We also increase more click-based checkouts, which has higher quality than impression-based checkout. And we don't cause any decrease in the other engagement metrics, and also achieve slightly in relevance gain. Given the query pin, this is an example. We observed that the top 10 product recommendations after conversion score introduced have more relevant pin. For this work, the next step is to train a multitask classification model the offsite conversion tags are highly correlated with each other. So the checkout data can be very limited. So the multitask model can implicitly augment data size and introduce inductive transfer learning to improve the data generalization by sharing the information between several tasks, such as clicks and add to cart. To prevent spamming merchants gaming our system, to improve the training training data quality is also very important. We also while we keep training the new model by adding new features, the freshness of the model is also critical. So we will make automatic training and the evaluation pipeline to update the model regularly. Okay, thank you for listening to our talk. I hope you enjoyed the day. If you have any questions, feel free to ask us. Thank you.
Thank you, Zhai and Weiran, for a fascinating talk on how ML is powering shopping recommendations on Pinterest. Let's welcome Zhai and Weiran for a live Q&A with us.
Hello.
Hi,
Hey, good
Zhai. Hi,
afternoon.
how are you?
Good.
Yeah.
So we have questions coming in for you. The first question is for Weiran. How do you deal with cold start issue in collaborative filtering?
Yeah, that's an amazing question. It's a classic challenge for collaborative filtering. So we managed to do that by introducing the more complex component for each tower. If you remember the slide, we combine both raw IDs and some features. So this is basically to balance the pure memoization where you have seen is a code star problem. If you don't see those, we can leverage the content-based features that we add to the tower structure. And also I would like to call out that one of the beauties that working at Pinterest is that we can take free rides from a lot of amazing peers we have. If you remember the amazing talk Andrew Zhai delivered on representation learnings, some of the features we add to that tower is basically all the XSAGE model representation pre-learned at Pinterest.
Awesome. Here's a question for Zhai. Have you tried learning to rank formulation list-wise with graded relevance label for conversion optimization?
Yeah, that's a great question. So yeah, so I think because this is the initial model, we basically train the point-wise methods because the training data collection and evaluation will be much easier and faster. And as the first step, we just assume that once the pin is clicked, the checkout is independent from other pins to be clicked. So we want to first try if this model works. But we will definitely use some learning to rank methods. Could be our next step to explore some new models to, for example, to model the entire space model like probability of checkout given impression, or just a CTR ranking model.
Awesome. That sounds really exciting. Weiran, a question for you again. You mentioned data massaging is critical to training the collaborative filtering model. Could you share what you've done to your models in terms of this?
Yeah, we have done a lot, but some of the focuses, one is to denoise the data. So if you remember, the ID-based model focused too much on the memoization, hence it could be so biased. So we put some kind of a threshold of co-occurrence. The other aspect we do for data massage is trying to do some importance sampling. For example, taking into account both the recency and also the pairwise action space between the two events, trying to capture the importance of the positive labels.
Awesome. Here is one more, and this is probably be the last question for this talk. This one's for you, Zhai, a little long, so bear with me. Have you tried training both the factors of probability end to end? What are the trade-offs involved? And what's the performance difference of the factorized model over directly learning the probability of checkout given impression?
Yeah, so great question. So we haven't tried to model the probability of checkout given impression directly end to end. As I mentioned earlier, that among the impressions, we only have a small fraction of clicks happen, and the clicks will become the training data of the conversion rate model, and only the checked out data will be used as positive. So it will be even smaller fraction of data. So because of the data sparsity problem that we actually modeled the probability of checkout given click and the click-through rate individually on purpose. Because we also believe that the overall checkout given impression is dependent on the context more. For example, when we have search, we have the search query, and in the home feed is more related to the user's feature. So we believe that the checkout clicks given impression will be better performed by using the surface specific model. And there's some other recent literature to use the multitask to share the parameters between the click-through rate and the conversion rate prediction. That's a very interesting thing that we probably will try out in the future.
Awesome. Thank you so much, Zhai and Weiran, for answering our questions. In our final lightning talk, we have David Liu talking about data management for ML in Pinterest. Take it away, David.
Hello, everyone. Today, we're going to take a tour of Pinterest's data management approaches for machine learning and how they've evolved over time. My name is David Liu, and I lead the machine learning platforms team. ML platforms at Pinterest are used by 200 engineers and data scientists for over 40 ML use cases. Many of these are very large scale with billions of training examples and tens of millions of inferences every second. The core challenge of many ML systems is ultimately managing data. As Pinterest scaled both in team size and number of use cases, we had to massively evolve our approaches. To explain the title of this talk a little more, we think of there as being 3 types of data in our ML systems. First, signals is possibly a Pinterest-specific terminology. For us, signals are a general term for any sort of data one team is providing to another. For example, it could be about pins, boards, or users. This data is often structured, and it may or may not be directly usable for machine learning. Features, on the other hand, are specifically for ML. They're a more restricted data type that can go directly into models to generate predictions, and they're usually derived from signals. Training datasets are large sets of examples for ML, and typically each example will have many features and some labels. In today's talk, I'll detail each type of data. We'll cover our early approaches, problems we encountered, and solutions we built. And finally, I'll mention our future work and the takeaway from our journey. We built our first signals in 2012 for Pinterest's search function. This was before we ever did any machine learning. An engineer built a MapReduce job that computed a structure called pin join. So this contained basic data like keywords, categories, and popularity. Each of these types of data is an example of a signal. People kept adding signals over time, like pin performance history, our content understanding, and image analysis. They added lots of versions of these signals over the years as well. So the structure grew to thousands of fields in a really complex and deeply nested structure. So this introduced a lot of problems over time with these monolithic data sets. First, the jobs to build these data sets became huge, slow, and unreliable over time. Issues would often affect all the signals simultaneously. Second is quality. Signal authors would eventually leave the company, and we weren't monitoring for freshness or quality, so data sets could go stale, sometimes for months at a time. It was really hard to pinpoint problems and to roll back data sets. Third is knowledge. We relied a lot on tribal knowledge to discover which signals to use, and old signals wouldn't be removed at the end of their life. To understand the signal's lineage or its usage, you would have to trace a lot of code. To solve these issues, we built a signal platform to provide a standard way for teams to publish and consume data in a modular fashion. Users provide two things to define the signal. First, they declare the business logic of their jobs. This is a set of Java functions that they write against an abstracted data flow framework. And under the hood, we'll run it on MapReduce or Spark. Second, they register the signal. They would define who owns the data, its inputs, a configuration for things like freshness and quality guarantees, as well as specifying how their data should be made available. Our platform will then manage execution of their signal whenever their inputs change. We'll handle storing the results and serving the data to customers. We manage the monitoring, metrics, and alerting, and we provide a UI called Signal Hub. Here's how that UI looks. It's a searchable catalog that keeps track of ownership information and signal status. You can explore the lineage graph and get a list of consumers of your data. You can view metrics like the freshness, QPS, and data quality indicators and plot them over time to investigate issues. There's a number of other functions. And today, over 600 signals are available in Signal platform. Migrating into this platform was a major effort that took over 18 months, actually. Required cleaning up years of accumulated tech debt in the form of unowned signals. Today, our ML feature store is built on top of the Signal platform. This way, machine learning features inherit all of these same data governance tools. In the next section, we'll see how the structures that we used for signals influenced our early machine learning infrastructure choices. So on to the second type of data in our systems, machine learning features. Our earliest models in 2014 were very simple, and as a result, most of the effort focused around manual feature engineering. The set of signals that we used as input, which we called raw data, was updated pretty infrequently. Our serving systems were built around this raw data. So each team would have a different thrift structure with a set of fields that they were interested in. We built a domain-specific language called Linchpin to handle this input. The DSL would specify how to extract features from thrift structures. For example, you could extract subfields or compute matching scores of different vectors. This engine was written in C++ to handle our largest ranking use cases with tens of millions of inferences per second. We really wanted to avoid training serving skew, so we put the feature extraction logic inside our models with this Linchpin DSL in order to guarantee the same features would be used in training and serving. This way, model inference would consist of simply appending a few operations to the end of the feature extraction logic. This system worked really well initially, but we saw problems later. Mainly, we really regretted using thrift structures as our input. The Linchpin models became big and hard to debug, and it turns out that building this new language was hard mainly because you need a lot of tools for a good developer experience, and we didn't account for the effort it would take to build those tools. A result of this was that teams were not sharing features, so successful ideas had to be tried on, once they were tried on one use case, would take a lot of effort to be added to other models. Our requirements also shifted over time. As we started using deep learning, we moved away from hand-engineered features, and we wanted to add new signals more often. So to solve these problems, we first standardized on a unified feature representation, or UFR for short. The key change here was to flatten the input to the models. So we'd only allow a restricted set of data types, primitives, vectors, or tensors. No more complex thrift data. The UFR would also indicate the feature's interpretation. For example, an integer could represent a numeric feature like the count of pins, or it could be a categorical value like a country ID. With these feature representations, all teams now had the same input format for their models, so we could ditch the complex Linchpin DSL. The conversion to model inputs is very standardized. As a result, the models also became much simpler. We adopted open source PyTorch and TensorFlow, which have become industry standard, and they have a ton of great tooling around them. Once we had this feature representation, we built a feature store on top of it. Each feature is identified with an ID, and they're further organized into entities. For example, user features keyed by user ID, pin features keyed by image signature. Next, we built many applications against this feature store, like standardized batch and online inference. Crucially, we can use the feature store to backfill training data with new features. This saved a lot of time as opposed to waiting weeks to collect new training examples with logging. And we also built a front end for users to explore features that they can use. This is a peek at the front end feature hub. We won't have time to detail it in this talk, but it also provides a lot of useful functionality. Finally, I'll touch on our third category of data management for machine learning, training data sets. Pinterest uses a lot of log data for training. Naturally, these logs arrive in a row-oriented format where each thrift object contains an event or a training example. And as I mentioned before, the nested raw data inside these thrift objects is really hard to deal with. So whether you want to downsample the data set, add in labels, or join in extra features, you pretty much always needed to write custom code. But once we used a unified feature representation, it becomes possible to have a much simpler data set representation, which is a flattened table. So each column becomes a feature, and the data types are simple enough to manipulate directly in SQL. We also switched to Parquet as a columnar storage format, which compresses the data much better, and it's a lot faster to read. Another problem comes up with training datasets, though. There's often a long set of operations involved in building the training data, like joins to get labels, subsampling examples, and backfilling new features. As the team gets bigger, people experiment with each of these steps, producing a ton of variations of pipelines. It duplicates the different jobs as well as the intermediate data storage. One solution that we built was a workflow system that we call EasyFlow. This is a data-aware workflow orchestrator. The engine will track the lineage of each data set reproducibly. So it tracks the inputs and parameters that go into making each data set. So now each user will simply declare the full set of steps that they need. The system will optimize for them, deduplicating multiple workflows that contain the same jobs and reusing their outputs. Our most recent approach further minimizes the number of copies of transformed data. We now maintain table groups that are joined as late as possible. And each use case has a master table with all the examples that might be used by downstream training. Each row has a unique key. So when different experimental models want to attach extra features or new labels, they can defer the join until later. Here's how that looks. We can maintain one production pipeline that gathers most of the features and labels. And if someone wants to build an experimental model with a new feature or a new label, then they can produce a table containing just that one column without duplicating the other data. This saves a lot of extra storage, and most of the transformations end up in a SQL query at the end of their pipeline right before training. So what's next? Our systems have come a long way, but there's still a lot that we'd like to do. For our Signal platform, we want to expand our tools to cover more types of data throughout Pinterest, especially as stream processing becomes more dominant. For our feature store, we need to better handle real-time features. They pose special challenges like time-correct replay and backfill. And for training datasets, we want to build shared training pipelines now that the training data has a standardized format. To close out, I want to leave you with a simple takeaway from our journey. The most important part of building a platform is defining interfaces. There's two reasons. First, standard interfaces enable people to collaborate in larger teams. We saw that the Signal platform enabled proper ownership, quality guarantees, and better knowledge of what's available. The feature store and tabular datasets also enable larger machine learning teams to share their work with each other. The second purpose of interfaces is for machines. These interfaces allow us to build more powerful tools, like the Signal platform, the feature store, model serving, and dataset management tools. So for machine learning specifically, it makes sense that the most important interfaces are data interfaces. Thanks for listening, and I hope you found this interesting.
Thank you, David. That was very insightful. Lots of interesting and insightful learnings from your talk. We see how bleeding edge ML and ML infrastructure has to go hand in hand, and one cannot happen without the other. On that note, let's welcome David for a live Q&A with us. Hi, David. Welcome. Thank you so much for joining us.
Hi, thanks for having me.
The audience is very excited about your talk, and we are seeing quite a few questions. Why don't I start with the first one? How do you know when it's the right time to invest in standardizing ML platforms?
Yeah, I would say when we started out, everyone really wanted to go as fast as possible in terms of just building up a very simple ML system for their specific use cases. But over time, as we saw more and more use cases pop up, there definitely started to be duplication across different applications. I think when we really realized that there was a lot of opportunity was when we saw the lack of feature sharing. So like Home Feed would try adding one feature to their model, but it would be months or even a year before the same thing would be added to like related pins, for example. And this limit in velocity was really because of the lack of standardization.
Absolutely. There's always a lot of scope for like standardizing and, more sharing of infrastructure across the organization. Here's one more for you. How does your feature store deal with high dimensional text and image features?
Yeah, so the feature store, by representing everything as this unified feature representation, aims to make the data types very standard, but those types still do include things like tensors. So you can represent an image as a tensor for an input. You can also have strings in the feature store as well if you want to work with raw text. However, most of the use cases we see usually have more derived feature types. And so it does work with both text, images, and other feature types. We just don't want to have arbitrary thrift structures, which are very hard to manipulate in a model.
Absolutely. There's one more for you. Are you planning to migrate all of your data to UFR? Is it compatible with all your models?
Yes. In fact, we are quite far along the way to migrating to this standard feature format. And it's had a lot of benefits already in terms of thousands of features in the feature store and being able to use our shared inference tools.
Thank you. And this probably would be the last one for this talk. With all the great innovations in ML platform at Pinterest, how would you compare the time to develop a new model at Pinterest now versus 2 years back? It's my favorite one.
Yeah, great question. So 2 years ago, in order to build a completely new ML use case, you would have to do a lot of manual work, setting up like serving clusters as well as data pipelines to upload your features into serving. And there'd also be a lot of troubleshooting in terms of making sure that your data is the same between training and serving. So it would easily take, I would say, months to bring up new ML use cases. Nowadays, because we have this standardized path, you can focus on just writing your PyTorch model and then exporting in the standard formats and putting it into our shared serving clusters. So easily be done within a week or two.
Absolutely. As an ML practitioner and an engineering manager leading, machine learning team, I am super excited about all of this innovation that's happening. And, thank you so much for all of your work. Thanks again, David. And this concludes our lightning talk session. I'd like to thank all of the speakers for their efforts for such fantastic talks, which highlight all the bleeding edge, cutting edge work that's happening on ML at Pinterest. We'll go into a 10-minute break. And when we come back, we go into a technical panel where we have our ML experts at Pinterest talking about how ML ties into Pinterest vision. Thank you, everyone.